So in the last class we have seen about 8051, how to interface analog to digital converter and digital to analog converter through ports is what we have seen in the last class. So now let us try to see the more features of 8051 which is used to which has onboard timers. In 8086 what we did is we have interfaced 8254. So 8254 is a timer IC. So that we interface to 8086 to facilitate, like to count external events or to provide timings and all. So let us try to see the same feature with 8051 microcontrollers. So today what we do in this 1.5 hour, first we'll try to see about the timer and why we need timer, and if you want to use it as a timer or counter, how to do programming with the help of examples. Okay, and after that we'll try to see how to interrupt 8051 microcontrollers. Okay, that's up to that particular point we'll try to see in detail, because the same features you can extend it to the PIC microcontroller in the next chapter. So now this is the basic version proposed by Intel 8051. Much more advanced modes and advanced applications you may get out of the onboard timers or on-chip timers of the Atmel microcontroller or PIC microcontroller is. But to give an idea, the basic idea, so now let us try to see how this timer is helpful and then how to use it for different applications. Now, why do we need timer in the beginning? So the first, let us see why we need timers. So you may have an application where you need to count an unknown quantity. So now let us try to take in this figure, like the bottling company, where you have to count the number of bottles. So then the arrangement what you can do here is here is a conveyor belt on which the bottles will be moving on a conveyor belt. So what you can do is here you can keep a laser, right, and then here you can put an LED. Okay, this is a photodiode kind of thing. So this could be a transmitter and this could be a receiver. So this transmitter will be transmitting the rays, and when there is no obstacle, the receiver is receiving the signal. But when the bottle is passing through it, so then the transmitter output or the transmitter will not be getting the signal. So the output of the transmitter can be considered as a high. And the moment the bottle passes on, when LED, okay, when the transmitter is sending the signal, then you may be getting the output 0. So based on the number of bottles, you may be getting a clock signal like this. So sometimes you want to count the number of pulses. So then we need a timer or counter kind of application. So here, to count the external frequency or the external events, we can use this timer or counter as an application. Okay, and then in every one of us will be using watches or your mobile phones in which you have a timer. which gives or which counts, it's not counts, which is used to produce a delay. So to generate a delay of required time, so then you will be needing these timers. And another example of timer delay is triggering a bomb. So after 6 minutes you have to trigger a bomb means you have to, you will set the time, and as the time, as the timer counts this events, and when it is, counting down, okay, or timing down, then it generates a pulse in the end of the required delay. So the important thing is here we will be how our watch generates, or how our watch synchronize our events. Similarly, the timer it generates a delay for a particular time, and then it generates a triggering signal or interrupting signal. That is what the thing is. So here also we use timers. Okay, we use timers. And the next application where we need a timer is if you have a robot and the robot has to travel in a given path. Let us try to take you design a robot which can follow white line or a black line. Okay, so now the speed of and let us take that is a race. The speed of the motor has to be made maximum during this period, but when it is taking a turn, the speed of the motor has to be getting reduced, or otherwise it will go out of the track. So what we do is we excite the motor with pulses like this. Okay, we excite the motor with pulses like this. So when the speed has to be reduced, we will not supply power to the motor, so then the speed of the motor will be getting reduced. So we need pulses of different widths. So that we are calling it as pulse width modulation. So through PWM, we generate this and then we'll give it to the motor coil or motor driver IC L293D, and then we will be controlling the speed of the motor. So here also we use timers to generate pulses of different widths. So that is pulse width modulation. This is one more application. So the next application is you need a different frequency waveforms. Okay, different frequency waveforms. Example, on the motherboard of a computer, you have different ICs, and different ICs are working with different frequencies. Now if you try to take your i3 or i7 processor, that may be working with around 2.37 gigahertz. Okay, but whereas the other ICs, they may be working with 100 kilohertz, right, and so on. So what we need is we will generate different frequencies which are required by the other applications. So then what we do is we will be using prescalers, prescalers to generate different waveforms. Now let us take, you have a clock signal of this, and then here by 8, the clock frequency if it is divided by 8. So this waveform also you can generate by using these kinds of things. So to do these tasks, as we explained, like counting an external events and generating a time pulse or time delay, and we need timers, and to generate PWM, pulse width modulation, and we need timers and counters, and to generate different frequency waveforms, then we'll be needing timers and counters. So this is the reason we are going to interface for in a microprocessor based system a separate IC which is 8253 or 54. But whereas on microcontroller, the timers are on chip. And one more thing is, these time delays we can generate through software. So software delay routine is what we call. Let us take an example. In 8051 microcontroller, it requires 12 cycles of the processor clock for executing a single instruction cycle. One instruction cycle means it takes 12 clock cycles. And if the 8051 microcontroller, if it is clocked with a clock frequency of 12 megahertz crystal, then the time taken for executing one instruction cycle would be 1 microsecond, and according to the timer for one instruction cycle is 12 by 12 megahertz, that is 1 microsecond. That means, here let me explain this point little. So let us take, this is what your microcontroller 8051, and microcontroller clock is of 12 megahertz. So the clock, this clock will act like the clock of the on-chip timer. So we will be dividing this clock by 12. So by 12 generally on 8051 microcontroller. So then each clock period can be 1 microsecond. Okay, right? So now, so the time for one instruction cycle is 12 by 12 megawatt, means around 1 microsecond. So now consider this case. So now let us write a program to generate a delay of 1 millisecond. So then you can write a program like this. Move R6 with 250 decimal number and R7 with 250 equivalent decimal. You can write, you can take hexadecimal equivalent, or you can mention D to indicate this is a decimal. So then decrement R6. So this function, this instruction is decrement and jump no 0. If R6 is not 0, then go to label 1, means be here. So 250, 250, 249, 248. So like that it keeps on decrementing, and until 0 it will be here only. So decrement and jump no 0, then be there only, and decrement R7, and if it is not 0, be here. Okay, right? And then a return, right? So after this could be a subroutine you can write. So when the controller executes this return, it comes to the original place. So now if you try to take this simple program, so here is 250 and 250, and when it is decrement and jump no 0, when it is not 0 of R6, until that be here and R7 be here. So decrement and jump no 0, any particular value of Rx, this label it takes 2 clock cycles. So 2 clock cycles means 1 clock cycle execution, it will take 1 microsecond, So now it will take 2 microseconds. So now repeating this instruction for 500 times, 250 and 250, and it will generate a delay of 500 into 2 microseconds, around 1 millisecond. So this is how you can generate a software delay, right? But the disadvantage of this particular delay is your controller will be keep on executing these instructions only. Because of that, the controller cannot be doing the other task. It will be just simply doing this only. This is software delay. And now similarly you can generate a delay of 1 second. So how, now let us try to see. Move R5 250, A call delay. So you are writing a subroutine, a delay. So here we are writing the same program what we have just now discussed. Move R6 comma 250, R7 comma 250, decrement and jump no 0, the R6 be here only, that loop 1 here only, and decrement R7, and if it is not 0, be here only, this is loop 2, so be here only, right? And then when it comes out of the loop, it returns here. Then again you are calling. So successfully 4 times we will be calling this. And this is for 250. So then now here if you try to see that 4 times you are calling and each is of 1 millisecond and 250 times it is getting executed. So 4 into 250 around 100 millisecond means this is 1 second delay. So you can write a simple programs like this to generate a delay of 1 second or any subroutines kind of thing. So but the disadvantage here is the software delay is not very accurate because we cannot exactly predict how much time it takes for executing a single instruction. And generally an instruction will be executed in theoretical amount of time, but sometimes it may advance or it may be retarded due to other reasons. So therefore it is better to use 8051 timer for generating delay in time critical applications. So this is what very important. So in time critical applications where little bit delay also, little bit timing is also important. So there in the cases it is better to use a hardware delay of 8051. Where timing critical is not a matter, then you can go for software delay kind of thing. So 8051 has 2 timers and counters, or we can use the same thing as timer or a counter. It has 2 16-bit timers, and we call them as timer 0 and timer 1. Timer 0 and timer 1. And each timer is of 16 bits. So 2 power 16, which is of 64,000. Okay, 64K is what we call. So you can count from 00002 to FFFF. 16-bit count you can go for. So here you have 2 16-bit timers. Timer 0 is of 16-bit, timer 1 is of 16-bit wide. And 8051 has an 8-bit architecture. Each 16-bit timer is accessed as 2 separate registers of low byte and high byte. So the registers associated with the timers of 8051, so timer 0 and timer 1 are the registers, and as 8051 is an 8-bit, so timer 0 if you have, then the 16-bit register associated with timer 0 can be taken as TL0 and TH0. And timer 1 could be as TL1 and TH1, TL1 and TH1. So the timer is accessed as 2 separate registers of low byte and high byte. It is low byte and high byte. And the special function registers relating to timers are, as we said now, TL0 and TH0 related to timer 0, lower byte and higher byte. And you can mention them as TH0 or TL0 in the instruction, or you can give the addresses of them, 8A and 8C, which is related to TL0 and TH0. And TL1 and TH1, 16-bit registers. Okay, so their addresses you can see here. And two special registers, special bit registers, they are TCON, timer control, and timer mode. These two registers are related to timers. So if you want to use the unchipped timers of 8051, then you need to know how to program these registers are. So the registers are timer control register and timer mode registers. So now let us try to see the programming of this special function registers. So timer 0 and timer 1 registers are of 16-bit. So like this, TL0 and TH0 of 16-bit registers related to timer 0 and timer 1. So they can be accessed as low byte and high byte, TL0 and TL1, TH0 and TH1. And they can be accessed like any other register, like you can write an instruction move TL0 comma 4FH. The data of 4H immediately you can move into TL0, or whatever is there in TH0 you can move into R5. So you can access these two registers. So how many registers are related with the timers? 4 registers. They are timer 0 and timer 1 related registers of 2 16-bit, which you can access them as 2 8-bit registers, TL0, TH0, TL1 and TH1. And then another 2 registers are timer control register and timer mode register is. Okay, right. So this is timer. So this is timer 0 register and this is timer 1 register. Okay, and T mod register is timer mode register, and this is used to timer mode register is used to configure 8051 timers. So both timers 0 and 1 use the same register, this T mod register, for their configuration. So this T mod register is an 8-bit register. The lower 4 bits are used for timer 0 and the upper 4 registers are used as for timer 1, as seen here. The lower 4 bits are used for timer 0, and the upper 4 bits of the register, T mod register. So the T mod register as timer 1. So now let us try to see the individual bits of this T mod register. So C by T bar. The C by T bar is a bit. Here you have 16-bit timer or counter. So if you want to use the timer, then you make this bit 0 and you make the timer 1 as a timer for timing application, generating a delay kind of application. You make this bit 0, or if you want to count the external events, then you want to configure this as an counter, then you make it as 1. So the C by T bar, if it is 1, then this will work as a counter, and if it is 0, then you can generate delay, so that means it will be in timer operation. And these timers you can program through software and hardware. If it is software, that means you want to start counting, or you want to generate a delay through instructions. by software, then this gate bits you make it 0, otherwise you make it 1. So this gate bit, if it is 0, then you will write an instruction for starting count or for stopping counts. For stopping the timers or counters, you can do it two ways. One is using software, the another one is using hardware. So software means this gate bit you have to make it 0, otherwise you have to make the gate bit 1. Clear? And if you want to use it as a timer, then make it 0. If you want to use this two timer or counters as counter, then you make it 1. And this M0 and M bar, these are mode bits. So 8051 timer works in 3 modes, 4 modes. One is mode 0, mode 1, mode 2, mode 3. If M0 and M1, if it is 00, then these are 13-bit timers or counters. 13-bit timers or counters. This is of 16-bit, but you can restrict the count up to 13-bit. That means 0002 1FFF. This is the maximum count you can go for. So you can use when M1 and M0 in mode 0, then you can use it as this M0 by M bar, you can use it as 00 and you can use it as 01. Alright? And if it is 01, then it is a 16-bit timer or counter. It is a 16-bit timer or counter. And here, when it is used as 13-bit timer or counter, then 8-bit timer THX with and TLX as 5-bit prescaler. So prescaling means, you can use the 5 bits of the TL lower as prescaling. 3 bits of TL and 8 bits of TH. This X represents timer 0 or timer 1. Okay? As when it is in 13-bit mode, we'll try to see this in detail one by one. So when M0 and M1 they are 0 and 0, then it is in mode 0. Mode 0 means it is a 13-bit timer mode. And in this 13-bit timer mode, it will be using the higher 8 bits and the lower 3 bits of the TL, okay, and then 5 bits as the prescaler. So I already gave you the prescaler thing. So the given clock frequency can be divided into different things. And 1, 0 and 1, if M0 and M1 they are 1 and 0, then it will be in mode 1. So mode 1 means it is 16-bit timer. So no prescale, only it can be used as 16-bit timer or 16-bit counter. And when M1 is 1 and M0 is 0, then it is in mode 2. In mode 2, it is called 8-bit auto reload. So what do you mean by this 8-bit auto reload means? The registers, you can use them as, now let us take, you have TL0 and TL1. So that means TH0. You can use it as 8-bit register, you can use counter. You can use it as 8-bit counter and you can use it as 8-bit counter. But in mode 0 and mode 1, once the timing or counting is done, then again you have to reload the value into the registers. But whereas, so now let us take, I started with TH0, 00, the same thing it will be copied in TL0. Then now if you start the timer or counter, then it will be moving from 00 to 01 and so on up to FF. And once FF is done, a interrupt is generated, timer overflow will be generated, and again this bit will be automatically loaded into TL0 again, and it will goes on. So this is auto reload mode. That means no need to reload the count which you want to go for, count the timing sequence. Okay? So that is auto reload mode. That means automatically this content will be moved into this, and it will be working as a 8-bit timer or count. And when M10 and M1 they are 1 and 1, then it is split mode. That means timer 0 and timer 1, you can use them independently when it is in mode 0, mode 1 and mode 2. But in mode 3, timer 1 uses the timer 0 bits. In combination they work. That is split timer mode is. So 8051 can be operated in 4 modes. They are mode 0, mode 1, mode 2 and mode 3. Mode 0 is a 13-bit timer or counter mode. Mode 1 is a 16-bit timer or counter mode. And mode 2 is an 8-bit register, 8-bit timer or counter, but with auto reload facility. And mode 3, the two timers they are not used in independently, but they used in combinedly. So now let us try to see the example. Indicate which mode and which timer are selected for the following. So now if an instruction move T mod 01, so 01 means here the 4 bits, D7, D6, D5, D4, D3, D2, D1 and D0. And D7 bit, is a software or hardware kind of thing. So now let us take, this is 0, 0, 0, 0, 0, 0, 0, 1. So here, this is, gate, gate is 0 means, it is software controlled. And D6 and D5 a timer or counter. So timer or counter means these are timing applications only. So when it is 0 and 0, this will be in mode 0 and this will be in mode 1. So this is the lower timer and this is what the higher time. So the timer 0 in mode 1, this is what the bits related to timer 0, this is what the bits related to timer 1. So the timer 0 is in mode 1. Okay, so this is 0, 1. When it is 2, 0, so timer 1 with mode 2. And when you are writing an instruction, move T mod 1, 2. So 1, 2 means D7, D6, D5, D4, D3, D2, D1 and D0. D7, so now it is 1, 2. So this is 1 and then this is 2. So that means it's 1, 0. So the timer 0 is in mode 2 and timer 1 is in mode 1. So this timer 1 is in mode 1 and timer 0 is in mode 2. So independently also you can use the timers. But this is not the case in mode 3. So mode 0 and mode 1, mode 0, mode 1 and mode 2, the timers, they independently there. Okay, so now let us try to see the hardware configuration of the timers. So the difference between the timer and counter is when it is configured in timer mode, this when it is C by T bar, when it is 0, then it is connected to the oscillator frequency. And the oscillator frequency is divided by 12, and that will be the clock frequency for the timer. So if it is worked with 11.09 megahertz, so 11.09 megahertz is divided by 12, which is of 1.008 microsecond, and that will be the clock for your timing applications. When C by T bar, when it is 1, then the T1 and T0 input pins of 8051, the 8051 has these two pins, T0 and T1, and you can use, so any clock signal is connected on this, then you can use this to count the clock pulses. So this happens when C by T bar is 1, and then this switch will be connected here. So the difference is, for the timers, the clock is of crystal frequency or external frequency, depends upon the C by T bar of the TCON resistor. If it is 0, then it takes the internal clock signal, and if it is 1, then external clock signal will be connected to the timers. Then now let us try to see what these are. So these are TR0 and TR1, timer run. So then the SFRs of, if you try to see here, so now let us try to see the hardware configuration of this timer. Now let us try to see. So the crystal frequency, when the timers are, when this are used as timers, then the clock frequency is from the crystal. So if the crystal, if it is 12 megahertz, then 12 megahertz is divided by 12. So this is what we give the clock for the timer or counter, right? So then 1 by 12 into 12 megahertz means 1 megahertz is the clock frequency of the timer which you are going to give. So then 1 by 1, there is 1 microsecond. And if the clock frequency of the crystal, if it is 16 megahertz, 16 megahertz is divided by 12, which is a 1.33 megahertz. So then 0.75 is the microsecond, is the clock period of the timer. And generally we use 11.0592 megahertz. So then 1 by 12 of this, that is 921.6 kilohertz. So 1 by 921.6 kilohertz will be 1.085 microseconds. So this is what the clock signal we are going to connect for the timers or counters, for timers. So then the clock frequency is divided by 12, and then if it is the clock frequency, if it is of 11.0592, then the clock signal will be around 921.6 kilohertz, and the time period of the clock signal will be 1.085 microseconds. Okay, 1.085 microseconds. So now this gate pin If it is 0, then you can do software control. So then the software control using instruction set B or clear, set bit or clear, you can make this gate bit 0 or 1. And for that, you have to make the TCON register timer bits 0 or 1. So that means the gate bit, if it is 0, then you can run the timers by instructions. And if it is 1, then it takes external clocks. So now let us try to see the hardware way of starting and stopping the timer is by using gate 1 in the mod register. Find the value of T mod if you want to program timer 0 in mode 2 and use 8051 crystal for the clock source and use instructions to start and stop the timer. So now if you try to see this, timer 0 and in mode 2, so timer 0 is in mode 2, then you will be having this control word. And the C by T bar is 0 and then gate is 0. So this gate is 0 you are making. So this is 0. So this is what the value you have to load into T mod register. The another register you have to know about while you are dealing the timers of 8051 is TCON register. In TCON register there are two important bits. This is TF1, TR1, TF0, TR0. So this is related to timer 0 and this is related to timer 1. If you want to run the timer, so then you make this bit 1, timer 0. So then if you make this bit to 1, then timer 0 will start timing. And if you want to make the timer 1, so if you want to make this timer 1, this TR1 bit 1, so then timer 1 will be in, it will be timing or it will be, so it will be in timing application. Okay, so let us take the timer 0 is used in mode 1. So this mode 1 is of 16-bit register. So it will be started, timing from 00 to FFFF. Then to make that, you have to make this timer 0, 1. And this you can do it with the instruction set B TR0. So when you write an instruction set B TR0, then this particular bit will be made 1 and then timer 0 can be start counting. And once it counts from 00 to FF, if there is an overflow, then this particular bit is going to become 1. And similarly with timer 1. If this bit, if you write an instruction set B TR1, then this timer will be started counting. Okay, right? And when it calls, now let us take if it is in mode 1, then it will be started counting from 00 to FF, and once it overflows FFF, then this timer flag bit will be set. So if it is set means what? The counting or the timing is finished. So 4 bits of TCON register are related to this timer applications. Okay, so I summarize. There are 4 registers, 2 16-bit registers associated with 2 timers, timer 0 and timer 1, and 2 other registers, one is T mod and TCON. So T mod already we have seen here, which are having 8 bits, and you can control these timers and counters using gate bit. So software control means you have to write 0, hardware control means you have to write 1 in gate. If you want to use this as a timer, then make these 2 bits 0. If you want to use them as counter, then you can make it 1. And you can use these 2 timers 0 and 1 into 4 modes: mode 0, mode 1, mode 2 and mode 3. Right? And then when gate bit we are making 0 and you want to start and stop your counter, then to another bits you have to consider, that is in TCON register. TR0 and TR1 bit for starting the timer, and TF0 and TF1 indicates the count is finished. Okay, and by setting this TF1 bit is. Now to summarize this, so now let us try to see the hardware details of this. So now when C by T bar bit is 0, then the clock frequency, the internal clock frequency will be connected to the timer, which is divided by 2. When it is used as a counter, then the signal on T0 and T1 will act like clock for the counter. Okay, or timer or counter. Then now let us try to see what is this. So now let us try to see this TR0 is 1, TR0 is 1. And now you made this bit, gate bits is 0 of your T-mod register. When this gate bit is 0 means you are going to do software control. When it is software control, this is not gate, this is 1. So when it is 1, irrespective of whatever it is here, this is an OR gate, you will get 1 here. So when TR1, you are making 1 by writing one instruction, set B TR0. Now let us take, this is 1, you are making gate bit 0. Then you are writing an instruction set B TR0. So then this is 1 in the TCON register. So when it is 1 and 1, this is 1. So when it is 1, then this is connected here. Then the timer, that means if it is in timer mode, the crystal frequency will be connected here. If it is in counter mode, then the external clock is connected to the clock of the timer or counter. And now let us take, you are using this 0, and then now let us take this TR0 bit is 0. So when it is 0, the output is 0. So then the switch is open. When switch is open, no clock for your timer and counter, then these 2 timers are getting stopped. Is it all right? So this is what the hardware configuration of on-chip timers. And if there is an interrupter on 0 or interrupt 1 pin, input pin, so when it is 1 and when it is 0, or now let us take, you want to, now when it is 1, then this is 0 and this is 1, and based on this TR1 bit or TR0 bit, so if it is 0, then it will be stopped, or if it is 1, then it will be on. So this is what the conclusion of the summary of the 4 resistors which we have seen. So here the clock will be internal or external. If it is counter, then the clock is external, and if it is timer, then the internal clock will be connected to the clock of the timer. All right. So now let us try to see the steps in programming of these timers in mode 1. It is in mode 1. So mode 1 is a 16-bit timer. Mode 0 is also same, you can go for it. So now mode 1, now let us try to see. So it is a 16-bit timer, then it 002 FFO is what it will count. So this 00 to FF will be loaded into TH and TL. And after TH and TL are loaded with 16-bit initial value, the timer must be started. So this timer must be started by using instruction setB TR0 or setB TR1 for timer 1. And after it is being started, and it will be started counting, and once it starts counting and finishes FFFFF, then it rolls from FFF to 00 and it sets the TF timer flag bit in TCON register 1. So each timer has its own timer flag register TF0 or TF1. Then this timer can be monitored. So then you can check this flag bit. If it is 0 or 1, then whether count is done or not, you can see. So when this timer flag is raised, one option would be to stop the timer with instruction clear TR0 or TR1. Then you can stop this. So in order to repeat the process, then what you can do is TH and TL must be reloaded with the original value. Again, it has to be loaded. Once it is done, it will be clear. So now let us try to see the mode 1 operation of this. So then initially this in timer application, the internal clock frequency is divided by 12. So then your C by T bar will be 0, and then your timer bit will be made 1. So when it is 1 and 1, so then you load the value of TL and TH with initial value of counting, and once the count is done, then your TF flag bit will be made 1. So you have to monitor this TF bit 1. And you want to repeat the process, then again you have to reload. So this T mod here, you make the gate bit 0. Right? So now let us try to take an example. So then what is the value has to be loaded into as an initial count? You can check it out. So here, if you are loading an hexadecimal number, FFFFF minus, now let us take, this is what the count you want to go for. And the clock frequency of the microcontroller, if it is of 11.059 megahertz, then each clock is of 1.05 microsecond is what just now I have shown. So how to load the initial value into the counter, now let us try to see by this program. So you just program the timers in mode 1 and to generate a delay of 1 millisecond. Now let us try to see this. So the crystal frequency is of 11.0592 megahertz, and now I want 1 millisecond is the delay. So 1 millisecond is the delay I want. Then divide the desired time delay by 1.059 microsecond. 1.059 microsecond means this is the crystal frequency. So it is getting divided by this. So 1 by 12 of 11.0592. So which is around 900 something kilohertz, and then 1 by that will be 1.059 microsecond. So I want to generate a delay of 1 millisecond, then divide the desired time delay by 1.059 microsecond. So now let us take, I want 1 millisecond time delay. So then divide this one by using 1.085 microsecond. So 1 millisecond, 1 microsecond, roughly the value will be around 1000 approximately. So then 65,536 minus 1000, if you do 6, 3, 5, 4 and 6. So this value in this is value in decimal, and it's equivalent hexadecimal. So it's equivalent hexadecimal. If you try to convert, then see The hexadecimal online calculator you can choose. So then 64,536 would be FC18 is the count, has to be loaded into the register. Is it all right? So this is how you, now let us take, I want to generate a delay of 1 millisecond. I repeat, I want to generate a delay of 1 millisecond. So then what I do is, the desired delay has to be divided with 1.085 microsecond, and that I have to subtract from the maximum, which is 65,536. So this is what the procedure we are doing. So I want to know what is the count to be loaded here. So which is 65,536 minus this into 1.059 microsecond. So if I want 1 millisecond delay, so then what I do is 65,536. Okay, the 65,536 equivalent hexadecimal is FC18. Right, so this is what I load into the register, which is here. YY will be loaded in TH and XX will be loaded in TR. So now let us try to see the program. Move. So now I want to generate a delay of 1 millisecond. So then here move Tmod. Tmod is 00 means timer 0 I am using in mode 1. Timer 0 I am using in mode 1. So which is, here you have gate bit, C by T bar, and then M1 and M0. M1 and M0, they are 00 means mode 0, but what I want in mode 1. So this is 01, and I am using them as timer. So then this is 0, and software control is what I am going to use. So this is 01. So move Tmod register 01. This is binary or equivalent hexadecimal is what you can consider. Right? Then you have to load the value which we calculated just now here. FC0 here, FC18 now. So TH0. So I am using timer 0. Okay, I am using timer 0. So then FC will be loaded in TH0 and 18 so will be loaded in TL0. So now if you try to see, the value which we got is FC18. So this 18 is loaded in TL0 and FC is loaded in TH0. And set TR0, set B TR0, start the timer. Okay, and here jump not below, that means TF0 is not 1, jump not below this TF0 here. So until once the timer it starts counting, and then once it overflows, then it makes the TF bit 1. So then jump not below. So if it is not 1, then be here. Otherwise, clear TR0. That means clear TR0 for stopping, and then clear TF0. Okay, and then return. So this is what a subroutine you can use to generate 1 millisecond delay. So we have seen a software writing of delay and hardware generating of delay of 1 millisecond by using 8051. Is this all right? We are using timer 0 in mode 1 to generate a delay of 1 millisecond. So this is what the example. Now, how to generate 2 millisecond delay? So what we do is twice so now I am moving the number 2 decimal in R6 and I am calling a delay, so which I have written just now, right? So then that will give me 1 millisecond delay, and decrement, and if it is not 0, decrement and jump, if it is not 0, then again loop, so loop is here, again it will call, so 2 times is what I call this. Then S jump main, so every time you have to write the same thing. So then you can use the same subroutine for generating 1 millisecond delay. So like that you can generate n number of times 1 second delay, okay, or any kind of delay you can generate this. Is it all right? So it is 2 millisecond delay generation by using 8051 timers. So this is timer 0. Similarly, timer 1 also can be made. So it is mode 1 operation of 8051, in which you can use this as a 16-bit timer. Counter I'll try to explain in the next slides. This is timer application of 8051 timers. 1 or 2 you can use. Now let us take this example. In the following program, we are creating a square wave of 50% duty cycle. Duty cycle means equal on time and off time. On P1.5 bit, means port 1 5th bit, I want to generate a square wave of 50% duty cycle. Timer 0 is used to generate the time delay. Analyze the program. So now the program is move tmod 1, means it is in timer 0 is in mode 1, which is 16-bit mode. Then move TL0 F2 and TF0 FF. Okay, this is what the initial count done. So now what will be the delay? So then you are calling a call delay. So then here you are calling a subroutine. So then in subroutine what you are doing is you are running the timer 0, set B timer 0, and if the TF0 is not becoming 1, then be here until it counts. Then you are clearing TR0 and clearing TF0 and you are returning back. Okay, and then here this CPL, that means this is what the time is complement this P1.5 low or high until this delay finishes. Right. So on for some time you are calling delay, and after some time you are complementing it, then calling a delay, right? So then if you analyze this program, then what will be the frequency of the generated wave? So then what you can do, you can use this, yeah. So FFF minus the count value is FFF2. So FFF2. Okay. So then you can use calculator. So here FFFF minus, what is the program? The FFF2. So the delay loaded is FFF2. FFF2. Just a second. So the value is FF2. TL0 is F2 and it is FF. So the decimal value, the hexadecimal value is FF2. It can't be FF, it's a minus, sorry. Yeah, so FF minus FF2, and if you try to see, you are going to get D. FF2 will be here F2 FH. So FF2 minus FF, yeah, anyhow that is correct only. So the D, and then the count value would be the D 0FF2. So the delay is here. You know, we are going to analyze the program. So you are going to generate a square wave of 50% duty cycle. So then what would be the frequency of the generated signal is what we are trying to see. So it is FF2 and D plus 1, then the value will be 0, right? So that means for this much time, so that means F2 FH. So F2 FH, D plus 1 is what you need to add, because in the last count it will be, you know, coming out of the loop. So then for that much time, that means D on E, that much time it will be on. So now CPL, you know, if it is high, it will be made low, complement, so low for this much delay. Okay, this much delay, then it is made high. Okay, so then it will come back. So come back here, right? And then S jump here. Then again it will load the value and it will complement port 15, right? So this is what the program is. So now if you try to analyze it, the T mod is loaded. FF2 is loaded in TS0 and TL0, and port 1 point is toggled for high and low portions of the pulses. The delay subroutine is using the timer. Okay, this is a timer 0 TR0. So you are making it TR0. Okay. So the sequence you have to understand is it starts with FFF2, FFF3, FFF4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Right, and then it makes it sets the timer 1. So then in subroutine, if you try to see here, so then you are setting the timer and you are checking the flag bit. So if the flag bit is not 1, so then you are being here. So then after that, what you are doing is you are clearing the timer and you are clearing the timer flag, and then you are coming here. For that particular time it is on, for this particular time this is off. So you can generate a square wave of 50% duty cycle by using this particular subroutine. So square wave generation using this, you know, you can know this is what the example you can consider. Okay, so port 1 of same. So the crystal frequency is this, and if the program which we have done, if it is dumped on the microcontroller, if it is 8051 or Atmel 89CF1, so then you will be generating square wave on this. So it's very simple. So move P10000 port 1, and then, you know, this is the control board. You have to write in T mode and set B P1.0 and A call delay, and you are clearing P1 A call delay and S jump main. So this is what the delay you are going to write. Okay, so this is FE00. then that particular time, so the time you can calculate. So I clearly explained, if I want to generate a delay of 1 millisecond or 2 millisecond, how can I do that is what you can see. Okay. And this is the program, same thing you can extend for generating 2 kilohertz square wave. So this is for generating 1 kilohertz square wave generation, and this is 2 kilohertz square wave using 8051. Okay, right? And this is 10 kilohertz. So all this depends on the delay which you are giving here. So port 1 is what you are using here. You can treat it as 8051, no problem. So here you try to see the delay. You are setting P1.0. P1.0 is what on the pin you want to generate a square wave. Okay. So now you see T mode, you are making timer 0, you are making in mode 1, and you are setting this and you are calling delay. So delay is FE00. So FE00, and then you are setting the timer is started running, and then it will run up to it will get overflow. So then you are clearing these two, then here set with P1.0, then you are returning here, then now you are clearing it and calling delay. So you can generate this. Okay, so roughly you can go like this also. Now the objective is what? To generate 2 kilohertz signal. So 2 kilohertz signal means the time period is of 1/2 kilohertz. So 1/2 means 0.5 millisecond. So 0.5 millisecond now. So 0.5 millisecond is what your delay. So 0.5 millisecond by 1 microsecond roughly. So 1 microsecond means 0.5. Right, 0.5 into 10 power 3, right, 0.5 into 10 power 3, which is of 500, okay, which is of 500. So 500 hexadecimal value would be loaded here. So 500 means, this is what the count value. Just now I have explained. So this 500 hexadecimal, 18. FC18 is what it is loaded, and then that will gives you 0.5 millisecond delay. Okay, so which is equivalent of 0.5 millisecond, not 0.5 millisecond, it is 1/2. 1 kilohertz means 1 millisecond, 0.5. 2 kilohertz, it is a 2 kilohertz. So 1/2 kilohertz. 1/2 kilohertz means it is of 0.5 millisecond. So 0.5 millisecond means correct, 1 millisecond. So by 1 microsecond, which is of 1000. So 500. Yeah, correct one. This is okay, absolutely right. And then this will be converted into hexadecimal, and that hexadecimal value is of FC18. Okay, that will be loaded here in TL0 and TH0. So this is how you can generate 2 kilohertz square wave. Similarly, you can generate 10 kilohertz square wave. Just only the thing is you have to change the count value. Is it all right? So now this is what the timing example. Calculate the amount of time delay in the delay subroutine generated by the timer. So now let us take, this clock frequency is this 1/12, which is of 921.6 kilohertz. So then each clock pulse of the timer is of 1.05 microsecond. So the resulting delay will be the number of counts into this. So the delay by 1 microsecond, that is what the number of counts. So the number of counts for rollover, FFFH minus FF2 means 0DH. So this 0DH means 1 will be getting added to that. Is it all right? So calculate the frequency of the square wave generated on pin 1.5. So pin 1.5 means the total number of cycles. If you try to take the total number of cycles of 28, so 2 into 28, each instruction it is like 2 clock cycles, means 2 into 28 into 1.05. So this is of 60.76 microseconds, which is of 16,458 hertz is what the generated. So this is how you can calculate the frequency of the generated signal. Now if the subroutine is this, the number of clock cycles, so the number of clock cycles into 2 clock cycles of this, then you can calculate the frequencies. Is it all right? And in mode 2, so it is an 8-bit timer but auto reload. So in auto reload, what it can do done is every time no need of copying the value. Once you load, every time it will copy, then the timer will be keep on running. That is only the difference. So it in an 8-bit resistor. The example, so the procedure is load the TMOD value register indicated in which mode. So this is in mode 2. Load the value in TH register initially and then start the timer. Once you start the timer, this TH value will be loaded into TL. And until this bit is not becoming 1, then it will count. So then again the TH value will be loaded into TL. Okay, so this is what this. So now one example of this, assuming the crystal frequency is 11.0592 megahertz, find the frequency of the square wave generator on pin 1.0 of the following program. Right? So now this is T mod is 20, that is in mode 2, 8-bit reload. So then move TH comma 5. So TH1 is 5, set bit TR1. So timer 1 you are making on. So then it will runs in this loop until this becomes 1. So then complement P1.0 and clear this and then SGEM back. Here you are coming. So now, so we notice that the targeted address of SGEM. Then the mode 2 we do not need to reload TH since it is auto reload. So 256 minus this 0.5 into 1.0 microsecond. So this is of 251 into 1.051. So which is of 272.33 microsecond is the high portion of the pulse. So since it is 50% duty cycle, the period will be twice. 2 into 272.33, which is a 544.67 microsecond. So then the frequency is 1.83597 kilohertz. It is in mode 2. Okay, so right, so this is how you can get the applications of this timers. So now coming to the counter programming, what we do is the counter programming, we make the TMOD bit 1. Then the counter counts up the pulses are fed from the 14th and 15th pin, which is of T0 and T pin of 8051 microcontrollers. So the difference here is you have to make the TMOD pin 1. You have to make the TMOD pin 1, and then the clock pulses on T0 and T1, which are 14th and 15th pin of the microcontroller, will act like clock of your particular things. So now you can take this particular example. So here, this is what your 8051. So 8051, this P3.5, there is one clock is connected. So now you count the frequency of the external clock pulses. The number of clocks is what you count. So then assuming that the clock pulses are fed into the T1, write a program for counter 1 in mode 2 to count the pulses and display the state of TL1 on P2. So now you see this is in counter application. So we want mode 0. So mode 0 here T1. So assuming clock pulses are fed on T1, write a program for counter 1. So counter 1 in mode 2. So counter 1 in mode 2 means here we have M0, M1, C by T bar, and then gate. Okay, so this gate, externally, this gate is 0. By writing software, we can make it on and off. So this is 0, this should be 1, and then this should be mode 2. Mode 2 means this is 1 0, right? So 1 0, this is counter 0. Similarly counter 1 0 1 1 0. So 0 1 1 0, counter 2 anyhow I'm not interested in. So load this value in TMOD, means which configures timer 1 in mode 2, and which takes external clock pulses by writing the C by T bar 1, C by T bar 1, right? So then move TH0, that means you have to start counting the external pulses. So you are just clearing TH1, right? And set B P3.5. So set B P3.5, you are making it 1 in the beginning. So make T1 input. So that means when 8051 is cleared, it will act like an output mode. So here you are giving input pulses to this port. So that can be made 1. So any bit you can make it 1 input by writing 1. This is what clearly I explained. So I repeat, 8051 port pins, when it is initialized, it will be initialized as output ports. So now I am giving my pulse here on P3.5. That means I have to read these pulses. So I have to configure this port as input port. So if I want to configure the port as input port, then what I do is I write set P3.5 so that it will be configured in input. So then run the timer 1 by setting this particular bit and move the TL1 into the accumulator and move the accumulator on port 2 where your LEDs are connected. Okay, and you check the TF1 bit. So if it is not 1, then you get it back here. Every time whatever all you are getting here, you just display. So you can count the pulses which are connected to P3.5 and then you can display that are LEDs. So then once it is done, then you clear the timer 1 and then you clear the timer 1 flag and yes, jump again. So then again you start doing the same. So you can use this timers of 8051 as input or output. Okay, you can set this like timer or counter by just this C by T bar pin. C by T bar pin, if you make it 0, then it will be timer, and then if it is make it 1, then counter. So timer or counter, the difference is external clock pulse is counted, or from internal, when it is timer, then it considers the internal clock pulses of 8051. So is this clear? So this is how it can be done. Okay, so these are the modes of operations of 8051. So mode 1 and mode 2 is what clearly I discussed. So here the conclusion is, so when the C by T bar is 0, then internal clock signal is connected. When it is 1, then external clock signal is getting connected. And software or hardware, you want to start or stop the counter, then that depends on the TMOD bit. And then at that time, when it is open means the timer is not connected. When it is closed means the timer is connected, and then it can be stopped or clear this particular timer is. Okay, so this is what the application of the timers of onboard 8051. So much more, okay, much more advanced applications are available with Atmel and seen the applications of 8051 on chip timers and controllers by configuring them the TMOD register, and then you have to know the bits in TCON register, and you can configure them as in mode 0, mode 1, mode 2 and mode 3, and then you can practice the similar kind of examples. Okay, right? So with this I'll stop today's class. In the next class I'll be discussing input program, okay, how to consider inputs from 8051 and keyboard is how keyboard is interfaced, and then how interrupts of 8051 works is what I'll try to discuss in the next class. Okay, is that all right? So thank you.